Hello, welcome back. In this segment, I want to talk about a simple problem related to computing the order of an element. Suppose you're given a group G. Let's assume the group is Z star P, okay, made of numbers from 1 through P minus 1. That's the meaning of Z star P. All right, and we are given an element A in the group. Suppose the element order is D. The question is, what is the order of A power K? All right, so we are given the element order A is D. That means A power D is congruent to 1 mod P. That's the definition of order. D must be greater than 0 to be more precise. And D must be the smallest D such that A power D is equal to 1 mod P. And we need to compute the order of A power K. Assume K is greater than 1. Even you can assume greater than or equal to 1. That's not a problem, but it has to be an integer. Okay. Let's assume order of A power K is E. Okay, what does it mean? It means this element power E must be 1. That's the definition of order. And we can just apply the rules of exponent. We can multiply the exponents. That's true in the group Z star P. In any group, we can do that. A power K times E is equal to, I can write 1 as A power 0 mod P, right? 1 is nothing but A power 0. And now you have two bases that are same. You have A here and A here. And in the previous segments, we looked at if you have congruence where the bases are the same, that means the powers must be same, but the mod must be changed to the order of the base. The order of the base is, remember, base is A, order of the base is D. That's the reason I have changed the mod P to mod D here. This is because we learned in another segment, if G power X is equal to G power Y, we can conclude X is equal to Y mod I, if I is the order of the element G. Okay, so I stands for the order of the element G. So in this case, in the place of G we have A, which means we need to look at what is the order of A. Order of A is D. That's the reason I changed the modulus to D. Our unknown variable is E. We are given K and D, and we need to find E. One solution, obvious solution, is E equal to 0. If you put E equal to 0, you get 0 left hand side, right hand side is also 0. But remember, E cannot be 0 because E is the order. So E must be a number greater than 0. So we need to look at the next solution. If A times X is congruent to C mod M, and GCD of A and M divides C, then we can find the solutions. There are M solutions. I'm listing a few here. If you know one solution is X0, the other solution is X0 plus M by GCD of A comma M. Next solution is X0 plus 2 times M by GCD of A comma M, and so on. Finite number of solutions will be there. So we can, I request you to watch the linear congruence segments if you don't know how this particular conclusion is arrived. I'm basically just instantiating this for this context. And I mentioned to you, X0 in this case is 0, because if you put 0, you get satisfaction on the left and right hand side. But 0 cannot be the solution because E is the order of A power K. So we need to look at the next solution, which is 0 plus M by GCD of A comma M. So in the place of M, we have D. That's why I put a D here. And in the place of A, we have a K. So we have a GCD of M comma D. Okay, that's basically the next non-zero solution. And remember, order is the smallest number. Therefore, I can stop here. I don't have to go through the list of all the solutions. So I can just stop here. So the conclusion is simple. If you know the element A's order, you can easily find the order of A power K. Well, all you have to do is just take the D, the element A's order, plug it in to this little expression, D by GCD of K comma D. You know D, you know K, you can easily find E, which is the order of A power K. We can quickly do a demo if you want to convince yourself this formula is correct. So remember this formula. E is equal to D by GCD of K comma D. I will also write it on the other screen very quickly. Okay, so let's do this now. Suppose we print the residue table of say number 11 and look at, for example, the order of the element, say 3. What is the order of 3? Order of 3 is 5 because 3 power 5 is 1. Okay, let's now ask the question, what is the order of 3 square? So what is order of A? Order of A is 5 because 3 power 5 is 1 according to this table. Okay, so let me write it this very quickly. Order of 3 is 5. What is the order of 3 square? So that means your K is 2, right? Okay, K is 2. So according to the formula that was discussed on the whiteboard, order of A power K is nothing but, this is the formula we discussed on the whiteboard. Okay, so what is D? D is clearly the order of A, which is 5. So this is D. So we have 5 by GCD of K is 2. This is 2. right? GCD of 2, 5. GCD of 2, 5 is 1 because 2 and 5 are relatively prime. So the order of the element is nothing but 5. Okay, we can check now. What is the order of 9? Order of 9 is 5 according to this formula. Let's go to the row number 9. As you can see, row number 9 becomes only 1 if 9 is raised to power 5. 9 power 5 is 1. Okay, this is nice. So the formula is valid. I mean, we checked for one number. It becomes more interesting if you try and look at, for example, order of 8. Okay, let's look at order of 8. What is order of 8? Order of 8 is 4 because only 8 power 4 is 1, right? So 8 power 4 is 1. That means 8 square. Okay, what is 8 square? 8 order of 8 is 4. That's clear. 8 square is 12 in mod 13. We need to find out the order of 8 square. So our question is to find what is the order of 8 square. Okay, so how do we go about it? Well, we have everything we need to plug into the formula and check this. So we can check that order of 8 square is 2. Okay, what is 8 square? 8 square according to this table is 12, right? What is order of 12? 12 becomes 1 if you raise it power 2. That's basically exactly what we have here. So 12 power 2 is 1. So we found out the order of 12 easily using this formula. That's basically it. Thank you.